So we are going to do all of Roman numeral 3 on machines. And there are a couple of example problems, so when we get to those, you may want to have your calculators out when we practice with the math a little bit. Okay. So we're going to start out. There are 6 basic types of machines. I will ask that you be able to list them. So whatever's highlighted is what you need to know. Okay. The part in green is just an explanation to describe each of those. And then on the next couple of slides, I'm going to show you pictures of each one. Okay. So a lever is kind of like a seesaw. It's very similar to when you balance the meter stick for the torque and equilibrium section. The meter stick actually acted like a lever. For an inclined plane, that can actually be used to lower or lift objects. If you needed to lower something kind of gently, you could roll it down the incline. But it's also helpful to lift things that are too heavy to actually pick up. So if you look maybe on the back of a moving truck, they have those ramps or inclined planes that come out the back because it's much easier to push something forward and then the ramp does the lifting for you. It's kind of hard to actually pick up maybe a washer and dryer and set them from the ground into the truck versus being able to push them, and then the ramp does the lifting. For a pulley, that's something that changes the direction of the force, and this is what your lab's going to be about. You will work with different pulley systems. We're going to start out with just one pulley, and you'll be able to see that you can apply a force down, and then on the other side, your object will be lifted up. And the purpose of a pulley is to change the direction of the force. And then as you'll see in the lab, if you can combine different pulleys together, it'll actually lessen the effort that you have to put in as well. So the pulleys are going to help multiply your force as well as change the direction and lift objects. A wheel and an axle can look like 2 different things. It can look like it's sort of an adjustable pulley where you have 2 different size rotating shafts fixed together, or it can physically be a wheel with an axle through it like you would see on a car. And then a screw, just a normal screw that you use to squeeze things together, or if you've ever used a C-clamp, maybe if you're gluing things together and you don't want to stand there and hold them and squeeze them until it dries, you can use a C-clamp. I put it's used as torture devices because it does have a tremendous squeezing force to it. So back in medieval times, they would put, it's called a thumb screw, so they put your thumbs in a little C-clamp and keep twisting it and tightening it. So just a little teeny force sideways squeezes really, really a lot, and it hurts. And then a wedge, that would be something where you can push down and you can get forces moving sideways. So if you had an axe that was splitting wood, the blade of an axe makes a wedge. So you would swing the axe downward and then the 2 pieces of the wood would go sideways. You can also use a wedge to prop something up or to keep it from moving. I don't know if you've ever seen like maybe mechanics or even just in a normal garage, they'll prop something under a wheel to keep it from rolling. That would be a wedge as well. So did you get a chance to write down everything you wanted to from that slide? Okay. So on the next one, we have some pictures. So I gave you an inclined plane. Okay, it's just kind of a triangle turn on its side. And then we talked about the moving truck as an example. For a wedge, you think about taking an inclined plane and just turning it to where the pointy part is down. So that would be like the axe splitting wood. A lever, look at the example. This time they have a hammer that's used to pry something open. Or if you think about maybe a crowbar that's used to pry objects, those act as levers. A wheel and axle, for this particular example, they used 2 wheels with an axle that connects them. The example of the doorknob actually only has 1 axle, so every time you turn a doorknob, you're actually using a simple machine. The screw, it shows you a picture of a physical screw like you would normally use to tighten things and hold them together. But anything with a threaded section, like the lid of a jar, anytime you open a jar and twist the lid open, you're using physics. That's a screw. And then that example of a pulley, we have the same example used right outside our windows. So if you look out and see the flags, anytime they raise and lower the flags, a pulley system is used to help change the direction of those. And then we have a quick quiz. Okay, what's this one? lever, about here. That's a bicycle chain thing around. It's like a pulley, but it's adjustable. Wheel and axle. Okay. This one? That one's obvious. And wheel and axle. Okay. Incline plane for the ramp, and the wheelchair itself is a wheel and axle. So on your test or quiz, I would describe different examples and ask you which of the simple machines it is. Seem pretty easy, hopefully. When you get to your Kia quiz, you'll notice that as well. It's going to give you an example and ask you what kind of simple machine it is. Okay, on the next section, I blackened out part of this. We're going to break down mechanical advantage and ideal mechanical advantage into parts. For all of your math problems that use machines, we're going to identify 2 forces and 2 distances. So your subscripts are going to be kind of important. I happen to pick the example of a lever because it's really easy to see. The effort force, I happen to draw that one pushing down on one side of the lever. The effort force is whatever the person does. So when you're reading the word problem, you want to look for the force that the person applies. That's going to be the effort side because a person puts in the effort. The resistance force would, in this case, be on the other side. That's the box that you're working against, and it's usually equal to the weight of the object. Okay. You won't have to worry about directions. What did you have a question?
Yeah. Why is the weight force pointing up?
It's the lever that's going to be lifting it up. Okay. I know like weight actually goes down, so that's why the lever's tilted that way. But when you push on the one side of the lever over here, as you push down, this side's going to lift. That's the only reason. Mathematically, you won't have to worry about positive and negative signs. So it was just to represent it in the picture. And the amount that you're lifting, it's kind of more like a normal force since it's the surface of the lever pushing up. But it's going to have the same magnitude as the weight of the object. So if you ever see kilograms, you are going to need to convert to newtons. Do you remember how to do that?
Mass times gravity.
Perfect. Okay, mass times gravity. So if you see kilograms, that's your mass. You want to multiply by 9.8 to get your force. So mechanical advantage, I'm going to scroll ahead a little bit. Go ahead and turn the page in your notes. We're going to jump mechanical advantage. So we drew our bottle. Okay. It takes normally 10 newtons to open it. That's your resistance force. That's too hard for you. So you're going to use a bottle opener. It only takes 2 newtons. Okay. What's your mechanical advantage? Good. Oh, close. What happens to the units? Oh, they cancel. Mechanical advantage has no units. Okay. Those of you that keep getting -1 on your test, yay! Okay, no units. Don't make any up. It's just a number. So in this case, by using a bottle opener as a lever, it's multiplied the force you put in 5 times. That's what mechanical advantage tells you. Okay, so this would be a case where it's not the weight, it's just what you're working against. Feel good about mechanical advantage? Does that make sense? A little bit? So in this next case, those are our forces. We want to do the same thing with distances. Okay. So I'm going to draw the bottle cap a little bit again. But this time it's partially opened. If you're not very good at drawing the pictures in your book. So I'm going to switch colors so it points, kind of stands out a little bit. From here to here, that didn't move very much. Okay, that's going to be our dr. Oh, didn't mean to move that. Sorry. Our dr is going to be called the resistance distance. Okay. That's how far the object actually moves. Okay. We started with the handle here, but we had to move it all the way up here. This would be our effort distance. So that's how far the person has to move the machine. So when we talk about the 6 simple machines, they can make things easier for you, but there's always an exchange. It was much less force for you to have to put in, but in exchange, you had to move that force over a longer distance. So we've got 2 forces, resistance force and effort force, and we have 2 distances, resistance distance, tongue twister, and effort distance. So a machine can make things easier for you because you apply less force, like we have here, but in exchange, you're going to have to move it over a larger distance. So there's a trade-off. And if you go ahead and flip back to where we were on the ideal mechanical advantage, we're going to look at a ratio of the distances. Yeah, sorry.
So when you do mass times gravity, that's the resistance force?
Yes, it is. So once you do the mass times gravity for the weight, that's the resistance force. So go ahead and flip in your notes to the next page where it says MA. This is called mechanical advantage. And this is going to be something that tells you how many times the machine multiplies your force. And then underneath that formula, I just wrote out the variables in words. So there's not exactly a definition for mechanical advantage, but you can think of it as it's going to be a ratio that tells you how many times the machine multiplies your force for you. Yes?
When would resistance force not be weight?
Let's say if you're trying to move something, maybe like pry open a big crate with a crowbar, it would be the force needed to open the actual crate itself. But by using a crowbar, you don't have to actually apply that much force to it. So it's the force needed to move something, like to physically move the object. And we'll go back and I'll use an example that's in your book as well. So we'll talk about that a little bit more. So let's say if we did have the crowbar example, if you were trying to open up a crate and it required 20 newtons to open it, well, if that's too strong for you, so you use a crowbar as a lever, and instead of having to apply 20 newtons to open the lid, you only needed to apply, say, 5 newtons to open the lid. Could you figure out the mechanical advantage?
4.
Yeah. Okay, so it would be 4. So you would take how much is actually needed, and that would be your resistance force, so that would be the 20 newtons. But by using a machine, if it only takes you 5 newtons, you just divide those two together. So the crowbar is actually multiplying your force 4 times. And we'll do a couple more examples too in a minute. So I'm going to go back to the other side of your notes. So on the next page,